Okay, all right. So this homework REC is gonna due on Wednesday night, which is tomorrow. And as you may see, there are three problems here. In general, I think the first problem is relatively easy. You can just take a look at those examples, trying to figure out what the problem really wants, and it should be pretty doable. Problem 2 is probably the most challenging one because that's where we start to handle that Sudoku problem. Okay, and problem 3, you just want to simplify the methodology you use to solve this problem so that you can get the answer a little bit more quickly. Okay, so I'm gonna start with problem 1. So problem 1 part A, this is just a this is something like a hint for part B and part C. Okay, so for those of you who have not started yet, you can try this code as I wrote in the description note. You can try this code and see what's the difference, okay, between the n and the floor n divided by 10 times 10. Okay, so if you do that, you will be able to see, for example, when I type it in my MATLAB, I get n equals to 814724. Okay, and the floor, that thing equals to 814720. Basically, if you subtract between these two, you will be able to get the last digit of this number. Okay, so I think this one just give you some hint to tell you how can you be able to separate a digit from a number. That's basically what it tells you. Okay, for part B, okay, they are asking you to write a function called dig to VEC. Okay, so I think part B is some sort of a special case of part C. Okay, because it asks you to use base 10. Okay, so an example is also given on the bottom of page 1, which is pretty easy to be understood. Okay, so as I mentioned in the discussion note, there are 3 things you need to consider before you can actually get this part correct. The first one is because this question asks you to use recursion. Okay, so you in that case, you need to use this dig to VEC instead of this function. Okay, inside this function. Okay, so first one you need to consider is what is the condition for running this recursion. Okay, so because you cannot run this recursion like for infinite many times. Okay, so you need to have some sort of condition for you to go to the next iteration. Okay, this is also very important for general recursion. Okay, you need to consider what is the condition for running this recursion. Okay, second one is how to get the digit from a given number. Okay, this is already given in part A. You should get some sort of idea about how you can handle this problem. For the third question you need to consider is how to update the input to that dig to VEC, because when you run the recursion, every time you run it, the input will be essentially different. Okay, so one thing you can consider is because this in part A already gives you how to get the last digit from a given number. Okay, so what you may consider is every time when you get this digit, you want to remove this digit from the number n. Okay, so next time when you run this iteration, you will be able to get the newest digit. Okay, so for example, if I get 24 as my n, okay, for first iteration, if I get the number 4 already, what I need to do is I want to remove that 4 from the number, so which it means essentially that n will be equal to 2. Okay, in that case, it's going to be very easy for you to split this digit from the number. Okay, so 3 questions. First, condition for running recursion. Okay, the second one is how to split a digit. Third one, how to update the input. Okay, so these are 3 questions you need to consider. Part C is actually very, very similar to part B. Basically, you didn't need to change most of the code, just make your code have more options, okay? That means you can have other digit, okay? So for those of you who are not, who don't quite understand what do they need for part C, you can take a look at the example on page 2, okay? So for example, if I'm telling you, if I use the code in line 4 as an example, they say dig to VECB 11.3, okay, this one. 11 is essentially the number, okay? And 3 is actually the base. So if you look at the result, 102, okay, because the first digit 1, it has the base 3 to the 2, which is essentially 9, okay? The last digit will have the base 3 to the 0, which is 1, okay? So if you add these two together, that will be 9 plus 2, which is essentially 11, okay? So just consider how you can generalize the code you made for part B. Another way of doing this question is start with part C to think about a more general case. If you can get C done, part B is just essentially a special case, okay? All right, so this is the end of part of question 1. So I think it should be pretty intuitive. And okay, so before I go to the next question, is there any quick clarification question that I can answer for question 1, everybody? Okay, I didn't see any response. So I will proceed to problem 2. Okay, so this problem 2 is basically they are asking you to write this auto Sudoku function in the end. Okay, so but this question the instructors have already like divided this big problem into many sub questions. So which actually gonna help you to get started. Okay, so for part A, well, actually before running part A, first you need to understand what is this like Sudoku puzzle. Okay, I'm sure most of you understand what's the problem, and I'm sure like you probably played this game like many times, like in the newspaper or magazine, something like that. For part A, first I think you need to understand the idea on page 3. Okay, so they have a 3-step 1, 2, 3. Okay, first trying to understand what is the like parent code, the parent node, the root node, and the child node, and also the leaf nodes. Okay, I understand that you have this covered in the lecture videos. So if you forget the definition, just go back and check the videos. Okay, so once you understand what's the logic for part A, you can go ahead with this non-leaf nodes. Okay, so this code should actually be pretty short. You see that the instructor said he wrote it with 2 lines. Okay, so I think there are 2 things that you need to consider, which actually correspond to the 2 lines of this code. The first one is how you will be able to get this linear index. Okay, just trying to think about how you got the linear index before in your previous assignment. Okay, and how to like check if there's a NaN in a given matrix or array. Okay, so these 2 should be pretty straightforward. Once you get a bunch of logical output of 1s and 0s, okay, you will be able to see, okay, how many unfilled elements are there in this given P. Okay, so and the next line would be, okay, so for every unfilled element, you'll be able to get 9 leaf nodes. Okay, so if you have several unfilled elements, the total leaf nodes will be essentially the combination of all the like this kind of different combinations within the unfilled nodes. Okay, so just think about what should be the final leaf nodes once you get the total number of unfilled elements. Okay, so just 2 steps. First, get the number of unfilled elements. Second, get the number of leaf nodes based on the unfilled elements. Okay, just remember for every unfilled element, you will result in 9 children nodes. Okay, all right. So this is part A. Should be okay. All right. So for part B, you are not supposed to write any code, but you may want to like type in your explanation or response in your script file, and this one will be hand graded. Okay. So for part B, I think you need to address the following problems, the following questions. Okay. First one is they give you this P1 array. Okay. First, you want to answer how many leaf nodes are there in the P1. Okay. So this should be pretty straightforward once you get the code in part A done. Okay. So just run the code, get the result, and put it in. Okay. So as you can imagine, because there are a lot of NaNs here, so you will actually result in a huge number of leaf nodes. Okay, so they want you to run some quick calculation about like if you can look at the leaf node at 1 billion per second, and they want you to like calculate how many centuries would it take to look at all leaf nodes. So this part is nothing tricky. Just like be careful when you do the conversion from second to minutes, okay, minute to hours, hours to days, days to years, years to like centuries. Okay, just make sure that you are not messing up between the conversion, okay, of two. And I think if you can get a approximate result, it should be okay, as long as it's not deviated from the correct answer too much. Okay, so this is the second question you need to answer. The third one is they give you another matrix, another array called C1, okay, in the middle of page 4. Okay, they ask you whether any of these descendants can be a solution. Okay, so I'm gonna go ahead and tell you that the answer is no. Okay, so because you see that the only difference between P1 and C1 is the second row and first column is a 2. Okay, but for a solution for the Sudoku problem, you want to have number 1 through 9 appear in every column. Okay, but you already see the number 2 happened twice in column 1. Okay, so just think about, okay, why that will actually result in a bad, which actually cannot be a solution. Okay, so just think about it, because you have 9 numbers and you want each of them to appear once. Okay, so if you have something appear twice, there must be at least one number that didn't appear in this column or row. Okay, so that's probably what you want to explain here. Okay, and I'm also trying to explain how this can help you reduce the computation time, because actually if you know something will not work, okay, at the middle of your calculation, you will actually be able to, okay, stop this direction without going to the very end and see, okay, this is not work. Okay, so that will actually tell you, okay, all the result following C1 will not be the solution. So you will actually be able to reduce a lot of computation time, okay, other than just trying to fill all the elements and take a look at the performance at the very end. Okay, so you can actually rule something out in the middle of your calculation. That's essentially the idea of part B. Okay. All right. So for part C, they are asking you to write several subfunctions for the final auto Sudoku function. Okay, so these are the functions that you need to use in the final auto Sudoku in part D. Okay, so I suggest you to be very careful, okay, about part C, because if this part is not correct, you will not be able to get the correct answer in part D, and you will have a hard time debug your code. Okay, because you have no idea where you are getting wrong. Okay, so what I suggest you is every time, okay, when you finish one function, just trying to test this function with some very simple, very simple test case. For example, you have a lot of P1, P2, C1, blah blah blah, those kind of array already given on P4, P5. This array given in your assignment. Okay, try to make the best use of them. Okay, for example, if you already finished the function reject on rows, just trying to give like 1 or 2 examples to this function and test. Okay, so for probably for the first case, you already see, okay, this will work. Okay, there is nothing violate the rules on on rows. Okay, probably the second one you have some wrong inputs of a given p. Okay, see if your function can distinguish between these two. Okay, so if you're confident about all the functions you write for part C, that's the right time for you to jump into part D. Okay, all right. So I will just go ahead and go over each of them. Actually, none of these are really hard, and so don't be terrified by those kind of long questions. Actually, each of them just requires several lines, like less than 10, I would say. And some of them just like 2 or 3 lines of code. So don't be afraid of that. Okay. So first function is reject on rows. Okay. So basically, the P input could be some sort of already filled array or array with some unfilled elements. Okay, so what you need to check is basically whether for every row, okay, for each of the row, what you need to check is whether there are any like kind of repeated inputs. So for example, if on like any of the row you see one number, okay, occurred more than once, that tells you basically you're having some problem. Okay, so in that case, you want to output the L to be true. Okay, just make sure that just make sure that you output the correct logical output. Okay, if you find some problem, okay, that's when you output true, because the function is called reject on rows. Okay, so if you can find multiple inputs within one row, your reject decision will be true. Okay, so that's basically the logic. Okay, I already write in the discussion note that the function unique might be helpful. Okay, just trying to type in MATLAB and see how this function unique works. Okay. The second one is called reject on columns. This is almost the same, okay, for as a reject on rows. So once you're done with the first function, you can like just copy and paste. And even easier way is just to transpose the input of your of this matrix P. Okay, so in this case, previously every row of the matrix P will be the column. Okay, the column will be rows. So okay, so in that case, you will be able to check whether the input the P matrix is valid. Okay, so I write on the second sub question, very simple code by transpose the input. Okay, and for the third one is reject on blocks. This is a little bit harder than part 1 and 2, because you actually essentially you need to consider how to get the inner 3x3 matrix. Okay, so basically, if you look at any of the example, there the P1, C1, or something like that, it's like a 9x9 array. Okay, so what they're telling you is they divided this 9x9 array to a 3x3 cell array. Okay, and each of the element each of the elements in the cell array is actually a 3x3 matrix or 3x3 array. Okay, so basically, if you look at C1 on page 4, okay, from the first row to the third row and the first column to the third column, this is essentially the first little 3x3 array. Okay, you want to consider. Okay, and the second one might be from the fourth row to the sixth row, but still the first column to the third column, and so on and so forth. Okay, so you will end up with 9 3x3 array. Okay, so what this rejection block tell you is you want to check whether in this kind of whether in each of the block, okay, you will be able to see multiple inputs. You will see multiple like numbers, same numbers. For example, if you look at the C1's case, okay, for the first 3x3 array I mentioned just now, first row to third row, first column to third column, you see that you already see the 2 twice, okay, in the 3x3 array. So that essentially tells you, okay, this C1 actually violates the rules for this blocks. Okay, so in that case, you would just get the output equals to 1. Okay, which means you can reject this input because of the violation of rules in the blocks. Okay, and the fourth function is just reject. Okay, so this is a simple one-line code. As far as you get the first 3 done, you can just use some sort of logical operators to connect these 3 results. Just be careful whether you should use OR operator, AND operator, or you should use like a mixture of these. Okay, trying to understand the logic of these 2 and what is the real output you want from this reject function. Okay, but I'm telling you that this is just a one-line code. Okay. For the 5th function is called first child. Okay, so this first child is actually has 1 input and 2 outputs. Okay, so the input, as is mentioned in this assignment, page 5, the input is still a 9x9 array whose element values represent a partially complete or fully complete Sudoku puzzle. Okay, so you have 2 outputs there, NP and IDX. Okay, so NP is essentially a let me see. Okay, so actually, if you look at here, if the NP and this IDX should actually return empty arrays if you find no NANs in this input. Okay, so that essentially tells you if this Sudoku has been filled. Okay, which means there's no unfilled elements, you will actually output the NP and IDX as empty array. Okay, so if the array has at least 1 NaN element, okay, the function should choose, like, be careful, it should choose just 1 of these NaN elements. Although you may be able to choose this unfilled element randomly, but I suggest you to choose this element using the linear index. Okay, so just choose, in this iteration, just choose the NaN with the smallest linear index. Okay, and what you want to do is return a new array, okay, called NP, okay, and also this IDX is essentially the linear index of the element that has been modified. Okay, so basically, for example, if you have if you look at C1, okay, on page 4, if the C1 is the input for this first child, a NP, what I suggest you to do is to change this, if you look at the third row in the first column, what you need to do is to change that n equal to 1, okay? And that is essentially the output of your NP, and the IDX is essentially 3, okay? Remember, once you find where you want to change the NAN, you want to modify that NA to 1, okay? This is already clearly stated in the assignment, okay? So go to the coding of this part. So for the first child, you may want to have a conditional loop because you first want to check whether the input is already filled or not. Okay, so this is actually some sort of conditional loop you want to add. Okay, and see if it is not completely filled yet. Okay, what I write here is you may be able to find this find function useful to help you locate the linear index. Okay, the locate that element, that NAN element you want to modify. Okay, so to summarize, first trying to see if it is filled. If it's not filled, okay, first make this matrix get the linear index of every element in this matrix. Okay, find the NAN with the smallest linear index, change the NAN at that place to 1, and return the new array to the output NP. Okay, and also return this linear index IDX. Okay, so that's essentially what you need to do for first child. Okay, so for the last one is called the next child. This next child is the code is also very simple. It should be like less than 5 lines of code. Okay, so first you still need to have a conditional loop. Okay, it's used to separate the two cases, where the first case is that the IDX is equals to 9. Okay, so that means you basically already tried all the 9 possible inputs of this specific position, because you want your the value at the IDX to increase from n to 1, 2, 3, all the way to 9. But in one iteration, if you see, okay, the value at that IDX is already 9, okay, so in that case you should just say, okay, so I'm done. I'm not gonna like run more trials for the specific position. Okay, so you will output the next child that NP is an empty array. Okay, but if P IDX is less than 9, okay, what you want to do is you basically return the same matrix, very similar matrix as P, but just change that P IDX, increase that value by 1. Okay, so still use that example on page 4. So if my input is the C1, okay, and the IDX is 3, for example, which means the third row and the first column. Okay, if the P IDX currently is 1, okay, what the output NP is nothing but a change that 1 to 2, and everything is the same. It's basically 2 to 2, okay, instead of 2 to 1. Okay, but when the input of C1 with that element third row, first column equals to 9, in that case, I will just output NP as an empty matrix, because that tells me, okay, I already tried all the possible cases for that specific position. Okay, so that's essentially all the sub-questions you want to write down for part C. Okay, and again, remember you need to test your code, okay, using the example before running, before going to part C or running the operator. Okay, and part D is the last sub-question for problem 2. They ask you to finally assemble this auto Sudoku function using all the sub-functions you write before. Okay. Okay, so so the instructor already said the helpful ideas is to get this recursive recall, okay, of this kind of auto Sudoku function. Okay, so what I suggest here is you first take a look at the pseudocode, okay, on page 6. The structure is actually already very clear. there are three different cases you want to consider in this auto-Sudoku function. Okay, the first one, if you look at the discussion note, is when the input G of this auto-Sudoku can be rejected, which means if you use this reject function, okay, it will result in a true value. Okay, so if you look at page 5, you write this reject function, which combines reject row, which reject column, and reject block. Okay, so that means if the input G itself is already, all its followers cannot be a solution. Okay, in that case, you can directly output this all solution cell as a 1x0 array, which means it is not possible to get a solution from the starting point of this G input. Okay, so remember to use the reject function for the first case. Second case is if G is filled but not rejected. That means G is already a complete array, and we find all the conditions for this auto-Sudoku is satisfied. Okay, so in that case, essentially G is already the solution. Okay, so this is the case for the second case. The first two cases are relatively easy. Just figure out how to write down the conditions. Okay, these are probably the trickiest part for the first two cases. Okay, the third one is probably the most common case, where G is a still valid but not filled array. Okay, so that means it has several NaNs in this input G. Okay, so in this case, they tell you still need to initialize this output. Or actually, I think you can initialize this output all solution cell at the beginning of this code, at the beginning of all the conditional loop. Okay, and well, you can also initialize it here, but just make sure that you initialize this output at the correct place. Okay, so that it will not be erased or affected by other possible cases. Okay, because you have three different cases. Okay, so for the last one, the third one, first you can initialize this output, and then you basically want to consider how you can run this recursion. Okay, so first, before you run to this recursion, okay, first you want to use the first child function, okay, because this one gives you the initial idea about where you are having those kind of unfilled elements, okay, and you want to start with the first one, okay, so this is the starting point of running into the recursion, okay, so first call the first child, okay, and then you want to consider what is the condition for running this recursion. Okay, so once you first call this first child, that's something like an initialization of this recursion. And then you may want to go to a conditional loop, either if loop or while loop. Okay, but you want to think about what is the condition for you to run this recursion, because you do not want to run this recursion for infinite many times, right? So clearly, an idea is you want to stop calling this auto-Sudoku or this recursion once there are no unfilled elements, right? So just take a look at the next child function, okay, and see whether it is possible to use the output of this next child function as some sort of conditions for you to continue run this recursion or break from this iteration. Okay, so but anyway, once you are done with the recursion, once you are done with the conditions, okay, you actually run into this conditions. You run this into this recursions. Okay, so in this within this conditional loop, like while loop or if loop, what you want to do first, you first definitely want to call this auto-Sudoku here. Okay, that's where that the recursion pops up. Okay, so you may want to have your output all solution cell equals 2. You can probably put basically you want to do the concatenating the all those kind of the previous output, the previous solutions and the solution that you get from this iteration. So you can probably get all solution cell equals to a bracket and put the previous all solution cell and also the result from this auto Sudoku and put the input here. Okay, and also like as I mentioned before, every time when you run this when you call recursion, you need to consider what should be the updated input for this auto Sudoku function. Because at the beginning, your G is the initial unfilled array. But every time when you try this iteration with try this function, you are actually starting to fill in something into the unfilled elements, into the unfilled location. Okay, so I'm saying that in this conditional loop there should be two lines. The first line is calling the auto Sudoku, and the second line should be calling this kind of next child, because that's where you are actually trying the different possible elements for a specific unfilled element. Okay, so and once you're done with all of them, you jump out of the recursion and you start with the next unfilled elements. That's essentially the logic you wanna consider here. Okay, so once again, for this auto Sudoku, three different cases. First one returns a 1/0 cell. If it can be rejected, use the reject function in part C. The second case, if G is filled and valid, actually output this G as a valid solution. Third one, if it is not rejected, but it is not filled as well, first call this first child to tell you, okay, where I'm having this kind of unfilled elements. Then consider what should be the condition for running the recursion. Okay, put it into a while loop or if loop. Okay, within this while loop or if loop, which means in this, like when you're running the recursion, first is to run this, call this auto Sudoku with a update array, okay, because you're actually updating this G array every iteration you are running this recursion. And the second line in this recursion is to use next child to update the array, okay, to update the input of this to the auto Sudoku for the next recursion. Okay, so just consider how you can implement this into your code. And if you are get stuck, you can type in the questions in Piazza or go to a supervised lab session and ask a GSI for a specific help. Okay, so and once again, once you're done for the question 2, try the examples before you run the autograder. Okay, so I think I'm done for question 2, and then I'm jumping to question 3. Okay. Question 3 is if you're done with question 2, question 3 should be relatively easier because you already know what's going on in this auto Sudoku function. Okay, so for the third question, first one as I wrote in the description note, make sure you understand the idea of easy fill. Okay, the idea is shown on page 7. Okay, you have those kind of 3 items. Okay, on page 7. Okay, so the idea is, for example, for the first one, for every for a given particular unfilled element in the puzzle, okay, the first thing you need to consider is for the row, okay, that this unfilled element locates. Okay, so yes, you are given the pseudocode. Yes. But the pseudocode is like they basically gives you the structure, but what I'm telling you is you need to like understand what they really means by if you look at the pseudocode line 10, if entry is determinable based on row, column, section. I hope you can understand what do you mean by one thing can be like determined. Okay, so the thing is like for every given element, look at the row where it locates and see what are the possible like inputs you can actually put into this position. Okay, because you need to remember you cannot put any number that already occurs in this row, and similarly you cannot put any number that already in that specific column. And also, you cannot put any number in that specific block, 3x3 section. Okay, so what that means is, okay, if you find, so there are basically three conditions. If you find there is only one possible choice for this unfilled element, in that case you can determine this number without running into some sort of loop. Okay, so that's gonna make your methodology less brute force but more efficient. Okay, but in terms of coding for this easy fill, as Mark said, the pseudocode is already given in page 8. In page 8. Okay, so you can just copy and paste the first several lines, keep trying those 6, 7, 8. You can basically copy these, and then so I think the trickiest part is how you can actually go to the how you can consider. You need to consider how you can get row and column indices for a specific unfilled element, because you first want to, because if you use the find function, okay, you will be able to get this kind of linear index, okay, and what you need to do is you need to convert those kind of linear index into some sort of row number, column number, okay, and you also you want to locate the 3x3 array where that unfilled element locates. Okay, so once you're done with this, okay, you can I typed in that set diff function in this discussion note. You can go ahead and check whether this function will be able to help you, okay, to find a possible choice of the unfilled element. Okay, so essentially the logic is, if you already know like what is the row number, column number, what is the block, you want to see, okay, what are the numbers that has not occurred in that row, in that column, in that block, and trying to see if there is any intersection. That set diff might be able to help you to find possible choices of the unfilled elements, okay, based on the row requirement, column requirement, and the block requirement respectively, okay? And once you know, okay, what are the possible choices for satisfying row requirement, what are the possible choices for setting the column requirement, and what are the possible elements for satisfying that block requirement, you may want to see whether there is any intersection, okay, whether there are any common choices. I write down here, you can use intersect this function. I think you use this function somewhere in your previous assignment. Use this intersect function and see if there are any common choices from the 3 criteria. Okay, and the last thing you need to see is if there's only one common choice or not. Okay, if you find, okay, there's only one common choice, that means that unfilled element is actually determinable. Okay, which means you can already see what you need to put into that specific location in your final solution. Okay, so in that case, just assign that value to the unfilled element, make the keep trying to be true, and running this while loop again, and trying to see if you can find the determinant element for the next unfilled entries. Okay, so that's essentially the idea for the EasyFill function. Okay, and once you're done with the EasyFill function, okay, so the last one will be writing this auto Sudoku Smart one. This is almost the same as the auto Sudoku. Okay, the only difference is you put a function called that EasyFill. If you look at the pseudocode on page 8, in line 6, you put that g equals to EasyFill g into that auto Sudoku Smart one, and essentially you'll just double check if you need to change something more, but I think that's probably the most important part you need to change in this auto Sudoku Smart one. Okay, the idea is every time when you given a new G, okay, first trying to see if you can directly fill in some of the places, because if there are only just one possible solution for that specific place, okay, and once you fill in all this kind of determinable elements, and that's when you want to jump into the those kind of iterations and use the same methodology you use for auto Sudoku. Okay, so the reason why this is smart is, first, like some of those kind of elements are already filled. Okay, so that means the number of leaf nodes is greatly reduced because you actually already remove some of the unfilled elements. And that's how you can make the code more efficient. Okay, and once you're done with this Auto Sudoku Smart 1, you may also want to try the last several examples, P3, P4, P5. Okay, they already give you some sort of hint. Both, like all of these three only has one solution. Okay, it should be very easy for you to get the result, because if you look at P3, P4, P5, especially P5, if you look at, there are a lot of NANs in this P5, and if you use this kind of brute force like method, for example, Auto Sudoku, you probably end up with a very long computation time before you can get a result. Okay, but if you use Auto Sudoku Smart 1, since you already get some element filled before you're jumping into the loop, you are actually going to be able to greatly reduce the computation time you need to get the solution. Okay, so that's basically the idea for the last problem of this homework. Okay, so I think this is what I want to discuss about this recursion homework. Remember, you still need to get this get a nice template, okay? And remember, you want to put some sort of explanation for part 2B, and that part will be hand graded. And remember to upload your homework before 11:45 tomorrow night. Okay, so that's all I want to talk about for recursion. I'm gonna go ahead and answer some sort of quick clarification questions about this homework before I take over, before I like give this host to the next GSI. Okay, I think there will be another GSI coming at 11, and before that I will be able to answer some quick questions.